Hi. In this work, we study sampled metrics for item recommendation. Evaluation metrics are used to compare the performance of two recommendation algorithms. Because the number of items to recommend can be very large, it has become common to compute the metrics on a random sample of items. In order for this procedure to be meaningful, one desirable property is that in expectation, the order of the metrics is preserved. We study this consistency property, and we find that, except for AUC, common metrics used in recommendation are not consistent under sampling. This includes precision at k, recall at k, and average precision. In the case where there is a single positive item per user, we can derive closed-form expressions for the expected metrics. This is illustrated here for recall at 5. The exact metric, in purple, assigns positive value to the top 5 ranks only, by definition. Under sampling, the expected recall has a smoother decay, which becomes worse with fewer samples. Because the bias depends on the distribution of positive ranks, the overall bias depends on the algorithm being evaluated. This explains why the ordering is in general inconsistent under sampling. Here's an example where we compare three recommendation algorithms, X, Y, and Z, on the MovieLens dataset. The x-axis is the sample size, and the y-axis is the expected recall at 10. Depending on the number of samples, different conclusions can be drawn. Here, x better than y better than z, x better than z better than y, or z better than x better than y. In this case, it takes more than 1,000 samples to obtain the correct order, which represents about 25% sampling rate. We also investigate what can be done to alleviate this problem. We define corrected estimates by minimizing different criteria, such as bias or bias variance trade-off. Here's the same MovieLens example with correction. In this case, the correct order is obtained with a sample size of about 60, much smaller than the 1,000 samples needed without correction. With this work, we wanted to bring attention to the potential danger of sampling during evaluation. Because the estimates that are commonly used have high bias but low variance, this can lead to apparent confidence in the wrong conclusion. For this reason, we recommend avoiding the use of sampling during evaluation. When that is not an option, the correction methods that we propose can alleviate the issue. Thank you for watching this short summary. For more details and additional experiments, we invite you to read our paper on sampled metrics for item recommendation.